In the article I shared, there have already been several comments. One of them, by Julian Gomez, was asking how to start looking into PPO, GRPO, DPO. I shared the idea that it is important, first of all, to understand the principles behind all of this, and that is reinforcement learning. You need to learn the fundamentals. It's a complex topic and could be the subject of an entire semester just to delve into it properly. Today I saw a joke someone posted here. Buy this book, even if you need to go into debt, but the author has shared it, right? So he's giving it away for free. It's an old book, but they released a second edition a few years ago, and it's a good resource, but it's very dense. It's very dense. However, it's a good resource if you want to delve into what reinforcement learning is. Beyond that, I want to share a resource I've mentioned, which is Parlina, an adaptive, dynamic, multimodal, and autonomous learning platform, developed with agentic AI. Here, I quickly set up a course on reinforcement learning to understand some of these principles. I'll quickly share part of that with you. The fundamental principles of reinforcement learning are what an agent is, which is a bit different from how one thinks of an agent in the context of an LLM, which is a loop that uses tools to achieve a goal. It's something similar but different, an environment and a reward system. The agent makes decisions about which actions to take based on perceiving the environment and learning from experience. The environment itself is what the agent interacts with, which could be an opponent. It could be a set of rules. It can basically be the context in which the agent is operating, and the reward is a numerical signal that punishes or rewards, depending on the results of the actions, which change from one state to another. And then that state transition brings a reward. Here is a mathematical description. Don't be intimidated, it's not that complex. This is talking about the expected reward, which is a combination of the immediate reward at the next point in time. So here we are at t, and here we are at t plus 1. Therefore, that next step, that next moment in time, comes with a reward. Now, to look beyond the next step, to look at the second step that follows, this would be t plus 2, which would also have a reward, but with a discount factor. And so it continues. Iteratively, it can be expressed as an infinite sum from 0 to infinity of the reward of one step, multiplied by an exponential discount factor. What does that mean? Let's say the discount is very low. When this is multiplied by itself 2 times or once, it will significantly reduce the reward of the second step, and even more the reward of the third step. So it will prioritize the immediate reward, whereas if gamma is 1, it will give equal weight to the immediate reward and the next ones and those that come after. This way, it balances immediate rewards if gamma is low, with an emphasis on long-term rewards if gamma is high. Normally, what one aims to do is maximize cumulative rewards over time, not just what is earned immediately. So here several terms are defined and an example is given. Let's say an example of an agent could be a vacuum robot. The environment could be the house, the obstacles, where the dirt is. The state includes sensor data. Where is the vacuum? The battery level, if dirt has been detected. The actions can be the different directions in which to move, whether to perform a cleaning action or return to the charging station, the dock. And the reward can be a point system, like awarding 10 points for picking up dirt, a penalty of 1 point for bumping into a wall, or a penalty of 5 points for running out of battery before returning. So with this, one can define a system that describes that type of agent. There are different types of environments: deterministic, where you always see the result of an action like in a game of chess, or stochastic, where there is a random factor like playing with dice or something similar, where you can't be certain of the outcomes of an action. This is 100% deterministic. This is completely random. Often it's something in between. Stochastic, but with some level of determinism. It can be fully observable, where people see the state, or it can be partially observable, like in a game where you don't see the opponent's cards. One can also describe the state or action space as something discrete, which consists of only certain values that can be taken, or continuous, which is more like movement through space, rather than just different squares where pieces can go. Here's an illustration that was generated about what I mentioned. The agent being the vacuum cleaner software, the environment being the space in which it moves, the obstacles, the states, and the different reward or penalty signals. Here we talk about some challenges of sparse rewards or incentives that are not aligned with what is desired, or about overfitting, essentially learning incorrect behaviors. And those are the 3 main components: the agent, the environment, and the reward. Then we can look at what a Markov decision process is. This is a mathematical description that forms the foundation of reinforcement learning. Markov refers to the Markov property. I don't know if you've heard of it. There are many things related to Markov, but in summary, it can be described as the future only depends on the current state and not on the history that led to that state. So just by knowing the state, one can model the probability space of the state one is in, regardless of how one arrived at that state. So, the components of a Markov decision process are the set of states, the set of actions one can take, and a transition probability function. This is where the stochastic nature comes into play. Let's say we have a stochastic transition. If you're in a room and you open the door, you have a 90% chance of getting to the next room, or a 10% chance that the door gets stuck. As you can see here, if you're not familiar with this type of expression, it's a type of conditional probability. The vertical bar represents this. So this is the probability of reaching a new state, S prime, given the state S and the action A. This way, you can model the dynamics of transitioning from one state to another, given a certain action. We have the reward function, which is the numerical feedback that can be a reward or a penalty, and that's what gives the system the necessary signal to learn what it should do. And I already talked about gamma, which is the discount factor that will calibrate whether the emphasis is more on immediate benefit or long-term benefit. As I mentioned here, 0 means it only cares about the immediate, 1 means it cares about the future, and almost 1 is, let's say, a balance between the future but with a slight preference for the short term. And then the example of what is called a grid world is often used, a matrix world where one can start somewhere, try to reach a goal, there might be some obstacles, and there are penalties for moving to prevent unnecessary cycles, and so on. This way, it can learn an optimal route to reach its destination. Alright, now we start talking about policies. In this context, policy would translate to a policy, rule, or tactic, which are like the guidelines for what to do. Here, the Greek letter pi is used, representing A given S, meaning, according to the policy, according to the rule, what action to take if one is in a certain state. So there can be different types of policies: deterministic, where the same action is always chosen given a state, or stochastic, where the action is chosen probabilistically. One might have a preference, but can still randomly explore other options. So the goal in reinforcement learning is to find the optimal policy that maximizes the expected cumulative reward. This expected comes from statistics, which is like the average. It's what one expects given the statistical analysis, what the average cumulative reward would be given the policy. To achieve this goal, we look at things like value functions, which can be state-based, meaning how good is it to be in this state? What is the benefit? What is the advantage or disadvantage of being in this state? Or action value function, which is what is the expected reward being in a state of taking some action? Basically, how good it is to take this action in this state. This would be the action value function. With these two, one can calculate what they call the optimal value functions, which would be the maximum value that can be obtained from a state, or the maximum value of taking some action in a state. That is the Q star. So this way you can determine the optimal policy if you can calculate, note, and learn all the values of the maximum rewards from any state or any action. Some equations describe this mathematically based on the sum of policies, state transition probabilities, rewards, and discount factors. And that is used with different algorithms like Q-learning, which are popular for optimizing these policies. So we can understand that, let's say, the value of a state is the immediate reward plus the discounted value according to gamma of the next state, averaged over all possibilities. That is basically an introduction to Markov decision processes. Then we can understand what policies are and what value functions are. A policy function, as I mentioned, is the probability of taking a certain action in a given state. This defines the agent's rules. What it will do depends on the situation, which can be deterministic or stochastic, as we discussed. We already talked about the value functions. This is just going into more detail. Talking about the optimal functions, we saw the optimal policy, optimal value functions, and how they relate, along with some examples. With all that, we can understand two different paradigms, one called on-policy methods, which is learning from the current behavior, and agent learning from its own actions as it takes them. Here we can see the first of these algorithms that we saw in those acronym soups, which is proximal policy optimization, which is an on-policy learning algorithm. As I mentioned, on-policy is when the agent improves its strategy, decision-making, using the actions that the agent itself is taking or has taken. So this is something that mainly involves initializing a policy, an initial set of rules, interacting with the environment using that policy, collecting data on states, actions, and rewards, calculating cumulative rewards, and the advantages of the collected data. And with those calculations, it updates the policy, updates the rules, using some method like gradient calculation. Then, the data used for that iteration of updates can be discarded, and with the new policy, interaction with the environment is repeated using the new policy. This process continues until the policy reaches a stable, good solution. Old data cannot be reused because it was generated by an older version of the policy. Therefore, the data must be discarded. These data are no longer useful because they were from the previous policy. And since we are learning on policy, we are learning what the results of the new policy are. What are the results of the rules we have? How good are they? What data do those rules generate? That's why we have to discard the old data every time we update it. This talks about the mathematics of calculating the gradient, which is like the multidimensional differential, to see how to adjust the weights of the policy rules to improve the estimated reward. An example of teaching a robot to walk starts with random rules. It falls quickly and you record everything: state, action, and reward. You analyze the data, look at the actions that provided more advantages and those that caused fewer disadvantages, and update the policy to improve the chances of better performance. Once the policy is slightly better, you try again with the new policy and repeat until the robot can walk. As I mentioned, each time the policy improves, you need to generate new data with the new policy. You can't use the old data because it was generated by the previous rules. So PPO is one of the most successful on-policy algorithms. Proximal policy optimization. It was introduced by OpenAI in 2017. It is widely used for its simplicity, stability, performance, and it has a clipping concept that adds some stability. This clip limits how much can be changed, because before, sometimes things were changed so much that a solution was not reached. And they also have a way to use multiple training batches with the same data, something that, as I just mentioned, is usually not done with on policy, but they do it in a limited way here for different batches. This is the PPO, simplified so you can understand a bit of what it's about. There are advantages and disadvantages. The main advantages are stability and safety, which can be crucial when predictability is very important, such as in self-driving cars, when continuous control is very complex, like in robotic movement, when it's easy or cheap to collect data, such as in simulated environments like video games or physics simulators, or when simplicity is desired. It's not good to use it when interactions with the environment are expensive, like with real-life hardware, or if you want to leverage large historical datasets, because if it's on policy, you can't use data from before the creation of the new version of the rules, or when you want to achieve something quickly. This then gives an introduction to PPO as well. Here it mentions a library that is available for use in reinforcement learning. It's something you could tinker with, and to implement this without writing the code from scratch, you can simply use a library. Now we switch to off policy. Off policy, in contrast, offers a powerful alternative that allows agents to learn about a target policy, meaning target rules, using data collected from a different rule called the behavior policy. So here, you can manage these two rules, the rule you are trying to learn and the rule on which you have data. This allows for the historical use of data, making it much more data efficient. So here we can look at different techniques like DPO, direct preference optimization, which is a type of off-policy method. Here, we mathematically discuss the pi target and the pi behavior, which are the policy we want to improve or evaluate, and the other policy that generated the data we are using. It is much more efficient. It is much more scalable. It has some challenges. If there is a difference in the states, the different norms, in the data that generated it, but in general, it is more favorable. Q-learning, which we saw earlier, is one of the most used algorithms for off-policy. And here is a mathematical description, as we had seen with Q-star, which looks at how to select the most advantageous actions and how that relates to the policy one is trying to learn. Another algorithm is what they call deep Q networks, which extends Q-learning with deep neural networks. It's more complex, but also more recent. So here we talk about DPO, something relatively recent that uses human preference data, similar to supervised fine-tuning. You have what humans prefer without needing to model a mathematical reward or use reinforcement learning. DPO is like something that sidesteps classic reinforcement learning. Traditional RL with human feedback, you might have heard of this. Reinforcement learning from human feedback involves having human preferences with pairs of outputs, and having a reward model that can predict those preferences. Then, reinforcement learning, like with PPO, is used to optimize the policy under that modeled reward. But that's complex and unstable. So DPO simplifies it by skipping the reward model and reinforcement learning entirely. It frames it as a direct supervised learning problem. Preference data is collected, human choices are modeled, and instead of having to learn a reward model and optimize a policy, DPO directly optimizes for the expected cumulative reward. This is used, for example, for fine-tuning a language model where we have a pair of outputs and a human preference favoring the more polite one. Here, we can compute the probabilities and optimize the policy to improve the relative likelihood of this response over the other. And this is repeated for all data pairs. The benefits are simplicity, no need to model the reward, stability, less risk of overfitting, efficiency, and it is completely offline. Static preference data is used. It also has its limitations. It depends on a reference policy that should not be too far from an optimal policy. Otherwise, the preferences might not correct it well. You need to start with a good model, perhaps with SFT. There might be biases in the data. You are limited by the data, and since there is no interaction with the environment, exploration is limited. You cannot explore beyond what is in the data. Therefore, DPO is good for fine-tuning, not for discovering new behaviors. Here, it talks more about off-policy. Here is a section on important sampling and policy updates. We already talked about off-policy learning. This discusses calculating the reward under one policy, but we only have samples from another policy. We can still calculate things using what is called importance sampling, which reweights each sample based on the relative probability of the policy. So this is used in reinforcement learning for different components of trajectory weighting. It is used in policy gradient methods. These are more advanced and mathematical topics. They are not essential to understand the principles, but one can start to grasp a bit about importance sampling. Here is some pseudocode to implement it. Finally, we can look at modern policy optimization algorithms. We already talked about PPO. This goes into details about PPO and clipping, stability, and the pseudocode. We also discussed DPO and how to use human preferences without having to model the reward. And here we have GRPO, which was highlighted in the DeepSeek paper we reviewed. The group relative policy optimization focuses on leveraging relative performance within groups of trajectories, which is very effective in multi-agent systems and in scenarios where comparative feedback is more reliable or available than absolute rewards. Focusing on relative improvements instead of absolute values is what gives GRPO stability in training, making it robust, especially when reward signals are noisy, sparse, or hard to define. So here it talks about why relative performance is important. What are trajectory groups, which are basically episodes generated under similar conditions like the same environment, the same time, the same team of agents, and looking at how much better or worse a trajectory is compared to others in its group. Here it then describes the algorithm. All the math is here. The advantages and motivations. It works well with ordinal or preference data, such as human feedback data. It also doesn't require precisely defined absolute rewards, just their relative performance, one compared to the other. It's more robust, it's more stable. That's why it has been a very popular algorithm. Here it talks about training an agent in a multiplayer game, and how would that be simulated. Here we compare it with PPO and DPO. In PPO, we have the absolute reward that we saw, that mathematical model. With DPO, we see pairwise preferences. With GRPO, we look at relative performance within groups. What we use for the baseline in PPO is the value function we saw, which is how good it is to be in this state, or how good it is to take this action in this state. DPO does not have a baseline. The baseline for GRPO is the group average. PPO is better for environments with very clear rewards. DPO for leveraging preference data obtained externally. And GRPO is better for multi-agent systems, batch comparisons, structured feedback. Here it is said that GRPO can be a generalization of DPO for grouping comparisons, instead of just looking at pairs, looking at groups. That's more than enough for now. We don't need a full course in RL, at least not at this moment. But I wanted to give you some orientation because it's a different topic. RL is considered the third branch of machine learning, beyond supervised learning or unsupervised learning. That might help guide you a bit on what those acronyms mean. What do those reinforcement learning concepts mean? The rewards. What are policies? And I wanted to introduce you to the Parlina platform. The advantage of this platform is that you can create a custom course. You can even do it in Spanish. If you want to delve deeper, say about GRPO, you just have to say Introduction to GRPO and Reinforcement Learning. And by saying it in Spanish, it will generate the course in Spanish. This creates the knowledge taxonomy for the learning path on what you want to learn. And you can already see the fundamentals of reinforcement learning, what we had already seen, the basic concepts of reinforcement learning. This analyzes the topics, the learning objectives, and quickly generates them, in this case in Spanish. The same course we saw is being streamed. Here, the equations and tables are shown along with the callouts. Additionally, we have the advantage of presenting multimodal information. Images are generated that can accompany the content to help understand different concepts. This way, one can also grasp all the other topics more deeply. Here, this is a specific course on GRPO, so you can delve deeper into any topic, look at a specific topic or a specific subtopic about anything we want to learn. So I will be sharing this platform so that everyone can benefit from it. I will do it in stages, starting with the people who are interacting and completing the tasks so they can have early access. This way, we receive feedback and can continue improving the platform while inviting more people.